Chapter 4, Section 4.1, Exponential Functions. In this section, we'll evaluate exponential functions as well as discuss the graphs and characteristics of exponential functions. We'll also take a look at the special natural exponential function with base e, and we'll apply exponential functions by looking at the compound interest formula. Let's take a look at the definition. An exponential function, f, with base b is defined by y equals b to the x, where b is a positive constant other than 1. b has to be positive and not 1. Now, the reason why b can't be 1 is then you'd have the function f of x equals 1 to the power x. 1 to the power x is 1 for all x, so that's just a horizontal line, and that's not an exponential function. If b is less than 0, let's say b is negative 2, I encourage you to try to graph the exponential function y equals negative 2 to the power x, and evaluate that for various values of x like negative 3, negative 2, negative 1, 0, 1, 2, 3, like that, and you'll see that it makes very little sense. So b has to be greater than 0 and not 1. And notice also that an exponential function is a constant, in other words a number, raised to a variable. That's an exponential function, whereas a polynomial function is quite different. A polynomial function is a variable, like x, raised to a constant, which is its exponent. So they could not be more different than polynomial functions. Very, very, very different. Let's take a look at an example. This exponential function models the average amount spent in dollars at a shopping mall after X hours of shopping. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? Okay. Since X measures the amount of time that we've been shopping at the mall, and 3 hours have elapsed, so X is equal to 3, we simply evaluate that function where X is equal to 3, substitute it very carefully into the correct position, which is the exponent, exponents first on the calculator, and then multiply by the number in front, and that will give us the amount of money, the average amount of money spent after 3 hours of shopping. Let's take a look at a graphical example. Example 2. Graph the function y equals 3 to the power x. So we'll do this by evaluating the function at various values of x. Here we've chosen several negatives and several 0 and positive number. It's good to sample both the left side and the right side of the y-axis to get a sense of what the graph looks like in the bigger picture. Okay, so when x is equal to negative 2, then we have 3 to the power negative 2. So 3 to the power negative 2 means 3 to the power negative 2 means, by rule of exponents, 1 divided by 3 to the positive 2, and that's how we're getting 1/9 there for the y-coordinate. In a similar way, when x is negative 1, f of negative 1 is 3 to the negative 1 power, which is 1 over 3 to the first power, which is a third. When the exponent is 0, any number that's not 0, 0 to the 0 is not defined, any number to the 0 power is always 1 by rule of exponents. And when x is equal to 1, 3 to the first power is 3. So we carefully plot those points, and we draw the smooth curve connecting those points. All exponential functions are smooth and continuous graphs, and they have many different properties from polynomial functions. Let's take a look at those properties. Properties of exponential functions, well, they come in two different types. They come in those that are called increasing functions. This is where your base is larger than 1. And they come in decreasing types. Here's the decreasing type, where the b value is a fraction between 0 and 1. That's because a number between 0 and 1 raised to a power becomes smaller, so the graph decreases as x gets larger, whereas a number greater than 1 increases as x gets larger, and that's why that's an increasing exponential. Okay? Well, whether it's increasing or decreasing, b to the 0 is 1, so the y-intercept is 0, 1 for either case. They also have the characteristics that they have horizontal asymptotes. Here the x-axis, or y equals 0, represents the horizontal asymptote. That's the case because when you evaluate, let's say in the previous example, say we evaluate 3 to the power negative 3. That's 1 divided by 3 to the third. That's 1 over 27. As x becomes smaller and smaller in the negative direction, let's say negative 10, that's 1 divided by 3 to the 10th, which is, well, very small. It's near 0. But it is not 0. But it is very, very small. So exponential functions that are growth always decrease but never touch the x-axis. They continue to get smaller and smaller, the y-coordinates do, but they never reach 0. In a decreasing exponential, such as this one right here, when x becomes large, the function shrinks because of the exponent is negative. And the same reason why we have horizontal asymptote for increasing, we have a horizontal asymptote for decreasing. I'll do an example of that later when we look at the problems. The domain of exponential functions are all real numbers. In other words, there's no number that we cannot substitute in for our exponent and end up with a y-coordinate. So the domain is always negative infinity to plus infinity. The range, though, is restricted because we never reach y equals 0, the x-axis, but any y value greater than that we can always attain. So the range has a restriction to be greater than 0, or the open interval 0 to plus infinity. Let's take a look at some more details. Natural exponential. This might appear to be a very strange definition. I suppose it is. The natural exponential comes up in biology, physics, chemistry, mathematics, economics, finance. It's in almost every subject, so it's something that you have to get a little used to. The statement here for the definition says that 1 plus 1 over n to the power n, as n becomes larger and larger and larger, in other words, as n approaches infinity, yields a particular number. This does not get bigger and bigger and bigger and bigger. And I very much encourage you to set up a table of n versus the value of 1 plus 1 over n to the power n, and start with, say, n is 1, and then go to n is 10, and then go to maybe 50, and then 100, and maybe 1,000, and finally perhaps 10,000. Actually evaluate this, and you will see that these numbers right here slowly approach the number 2.71828, this number that's described here in the PowerPoint slide. The larger the value of n, in other words, this here is describing as n approaches infinity, as n gets larger and larger and larger, the value of 1 plus 1 over n to the n approaches this special number. This is an irrational number. It doesn't repeat, it doesn't terminate, and it has its own designation as the letter e. So just like pi has its designation to be an irrational number that doesn't repeat or end, e is another number. Pi is about 3.1. E is about 2.7. So the function f of x equals e to the x is called the natural exponential function, and it's called that because in most applications involving science and biology, the natural exponential models things in a much better way. Let's take a look at an example. Example 3. This exponential function models the gray wolf population of the western Great Lakes. F of x is the measurement of the wolf population, and x is measuring the time, specifically the number of years, after 1978. Project the gray wolf's population in the recovery area in the year 2012. Okay. First of all, when we model functions using time, we measure time from this point right here. So this point right here, 1978, we assume 1978 will correspond to t equals 0. We always measure time from a reference point and don't use dates. So 2012, how many years later is that? That's t equals 34. So we'll take the function and we'll substitute in 34 for our variable x. Right here it is done. And then very carefully we'll compute this. Depending upon the type of calculator that you have, you may have to first take e to the power and then afterward multiply by the number in front. I would suggest that on a calculator that you do it this way, e parentheses, input the number, and then hit enter. And this will make sure that everything you enter here in the exponent is the exponent to e. Then after, multiply by 1066. So we get the value 4446. Since it's an application problem, we should summarize this in a sentence. The 4446 number indicates the gray wolf population in the year 2012. And that's the projection 34 years later. Let's take a look at a different way to apply exponential functions. Compound interest. After t years, the balance A in an account with principal P, principal is the amount of money that you initially put in the account. A is often called the future value, which is the amount that you will have in the account after some period of time. Here that period of time is t, measured in years. You get an interest rate, R, applied to your money, always written in decimal form. And then we have compounding periods. This is the number of times that the money earns interest throughout the year. So this is our formula with all the letters substituted in, and a different type of compounding using the continuous exponential number e, so it's called continuous compounding, is a equals pe to the rt power. You can almost see the previous definition of the exponential right here, and that is part of the reason why this changes to the exponential number e for continuous compounding, but there is a bit of math involved to derive this from here, and I won't go through that right now. Let's see how this is applied. Example 4. Let's take $10,000 to invest. That amount is P, your principal, at an annual interest rate of 8%. Remember that we have to have R in decimal form, so in the formula, we'll write this as 0.08. Find the balance in the account, that's the A, the amount that you'll have in the future. After 5 years, that's the value of T, subject to quarterly compounding. So quarterly compounding means 4 times per year. If it were monthly compounding, that would be 12 times per year. Daily compounding would be 365 times per year. So we'll take our formula, here it is. We'll substitute in the initial amount invested, that's $10,000. The interest rate as decimal, 8% is 0.08. Quarterly compounding, 4 times per year, so the value of n is now 4. And then our exponent is n times t. N is 4, and t is 5 years. So depending on the calculator you use, you may have to do this in pieces. If you do it in pieces, first take this and add it together. Then second, raise it to the exponent. And then lastly, multiply by the 10,000 in front. So approximately, the balance after 5 years is $14,859 and about 50 cents. Now, what would happen if we try the continuous exponential formula here for continuous compounding? This would mean that the compounding is happening at every moment in time. And you think that that's the case, you would have an unlimited amount of money that's accumulated, and it's not true. You get a slight bit more, but not a lot. Let's take a look at an example of continuous compounding. We'll use the same problem in the same setting with the same numbers, except we'll change quarterly compounding to continuous compounding and see what happens. So this is example 5. PE to the RT, principal is still $10,000. The rate is still 8%, so R is 0.08, and T is the same, being 5 years. So first, take e raised to the power, and then multiply by 10,000. So now we have $14,918 compared to, where were we before, $14,859. So it is a small bit more with continuous compounding, but not a huge amount more. Of course, the larger the interest rate, the more time that you allow the money to accumulate interest, and the larger the initial principal that you put in, the greater the difference between continuous compounding and compounding that's not continuous. So the balance in the account after 5 years, subject to continuous compounding, will grow to this amount. And by the way, in the financial context, if you started with $10,000 and later you have $14,900, the difference between these two numbers, the starting amount and the ending amount, is the amount of interest that the account has earned over that time period. That's the end of section 4.1 PowerPoint.